Okay, class. Greetings from Morocco. Today, we're going to cover the chapter 6, which is on diffusion, and we have the following learning objectives. We're going to identify the needs for diffusion in real engineering applications. We'll talk about how it works in terms of atomic motion, and we'll get the equations that govern the rates of diffusion. We'll describe how it's a thermally activated process, just like so much else in material science. We'll predict whether vacancy or interstitial diffusion is faster. And eventually, at the end of class, we're going to get to Fick's first law and Fick's second law to actually describe diffusion under different conditions, one being steady state and one being non-steady state conditions. And if we have time, we'll get into some other conditions. But before we get to any of this, we are going to need to ask for a volunteer, somebody who's willing to risk life and limb for the sake of science. As soon as the TAs have picked somebody, I'm going to ask them to pause the video while they do the next demo. Okay. Now the class probably smells like a junior high school dance, but we're ready to learn about diffusion. So let's go back a minute and recall the case of case hardening. Case hardening, or carburizing, we did that to improve the fatigue properties of materials. It basically put the surface under compression so that these surface cracks, which are the problematic ones, are more difficult to grow. And we could do that in a couple ways, right? If you remember, we said you could put it in the presence of carbon, and the carbon is going to diffuse into the steel. But there's a lot of unanswered questions about that. For example, how do you control the thickness of that carbon-rich layer? How thick will it be? How hot should you heat treat it? How long should it be for? We haven't yet learned how to answer those questions yet, but this chapter starts to answer some of those questions. And before we can really dive into it, we have to answer the fundamental question of what is diffusion and how do we make it happen? Another question that we'll be able to answer has to do with the eutectic. We know that if you cool down an alloy at the eutectic composition, right there, as soon as you cross the eutectic reaction, that you get this lamellar structure, right? This sort of zebra stripe structure. But again, we have some unanswered questions. We know what the composition is of the black and the white phases. The phase diagram tells us that we basically have pure gold over here and we have pure silicon over here. But diffusion dictates how thick these regions are, right? How thick are these lamellar regions? It all depends on diffusion because you've got your gold and your silicon atoms, which are initially mixed together in some ratio. But then, after the eutectic reaction, these split, these things have to diffuse so that all the gold atoms are on one side and all the silicon atoms are on another. And so there is literally a distance, this distance here that they're going to have to be diffusing, and that distance that it's able to diffuse is going to dictate the thickness of these lamellar structures, and that depends on the diffusion coefficient. Okay, so there's many other applications like this where it becomes important. Let's see. Let's start by talking about diffusion in terms of atomic motion. And to do that, let's imagine a scenario. Imagine that you weld copper and nickel bars together, right? You start out with a pure bar of copper and a pure bar of nickel, right? You weld them together so they're stuck together. Imagine what the profile is going to look like in terms of concentrations. The concentration profile might look something like this. If we're looking at percent copper, and this was our copper bar, initially it might look something like this, 0 and then 100, right? But after some period of time, if you were to heat this thing up after you welded it, it actually might start to look a little bit different. It might look like the following. Right? Some of these atoms are going to jump over here. They're going to move down the concentration gradient. We know that atoms move down the concentration gradient as the demo from earlier showed us. And if you do this for a longer period of time or at a higher temperature, generally your curve might start to look like that. It's going to slowly start to even out. Right? So we see evidence of that where, again, initially you've got the two different atoms separate from one another, and as you heat them up, they're going to slowly diffuse into one another. So an interesting way to think about this is in this demonstration here in this video. You can see that if you have a lattice and you introduce a concentration gradient, so you've got one atom present on one side. Here we go. So they're more concentrated on the left in this diagram, and if you allow these things to vibrate, they're going to naturally spread themselves out in this lattice. They're going to slowly, over time, spread themselves out and slowly diffuse and reduce the gradient in concentration. So again, what's driving them spreading out is them wanting to reduce the gradient in concentration, or in other words, the concentration gradient is the driving force here. Now it's helpful for us in this class to think of this as a thermally activated process. So let's go ahead and do so. Let's imagine that you have an atom, and if you had an atom sitting right here, let's change color so it's easier to see. If you had an atom occupying this site right here, and you're talking about it hopping over there, let's draw that as an energy landscape, right? So here we have energy on the y-axis, and we've got distance on the x-axis. That's distance x, right? So this hopping distance between these two sites, that distance, let's call it lambda. That's our distance between these two sites, okay? And then if we plot this in terms of energy, the energy profile would look something like this. Basically, you start out at a lower energy, but then as this atom has to squeeze past the two atoms to go to this empty side over there, it's going to have to go up in energy. It's going to have to crowd those two atoms. But then once it's past those two atoms, it's going to go back down in energy, right? Therefore, we could say that this distance in this change in height there, let's change color again, this distance from there to there, we could call that delta G sub m. Or in other words, that's the activation energy for us to jump from one site to another. And if there's no driving force for this, meaning that there's no difference in the concentration, then the rate at which atoms move from one site to another is going to be calculated as follows. If this is site number 1 and this is site number 2, then there's no advantage if you're here versus here. Those are at the same height, right? Therefore, the rate of atoms jumping from site 1 to site 2, which we will call dN1 dt, is going to be equal to the rate of atoms jumping from site 2 back to site 1, which we'll call dN2 dt, right? Those will be equal to one another because this distance, this activation energy, if you will, delta Gm, is the same for both of these, right? Therefore, in mathematics, we say dN1 dt equals dN2 dt. That's equal to Vf times the exponential of the negative activation energy for jumping from one site to another over kBt. V is going to be the attempt frequency. So if you heat this thing up and the atom is vibrating more and more at higher and higher frequencies, then that is going to increase your odds of jumping, right? F is the fraction of atoms in the correct configuration. And this is taking into account geometry, basically. You've got these different sites, right? Imagine that you've got this setup. That's a vacancy. These are all atoms. So if you're talking about going from site 1 to site 2, F basically takes into account what's the fraction of sites that are available, that are in the right configuration where there's an empty spot, for example. Okay? Now let's reconsider this scenario, but this time with a chemical potential gradient driving force, and now this is going to bias flux. Flux is the flow of something per area per time. We're going to come back to that a lot. So now we draw this picture and it looks like the following. Here's our energy landscape versus X, energy. As we go from site 1 over to site 2, we have the following. We start out up here. There is an activation energy, but we're going to end down here. Or in other words, because there's a gradient in the concentration, the rate at which we travel from site 1 to site 2, that's dN1 dt, that's going to be much greater than dN2 dt, right? Because this activation energy is all that we have to overcome as we move from site 1 to site 2. Again, that's equal to delta Gm. But then this different distance in height right there, that would be equal to what we're going to call delta mu. And that is the difference in our chemical potential. So mu. Which again, if this is our jump distance lambda, and you know that there's a gradient in chemical potential, then this is equal to lambda times the gradient. So the upside down triangle is a gradient times the gradient in our chemical potential. Okay, now we can go ahead and actually put numbers to this. We can calculate jumping forwards from site 1 to site 2, and it's going to be dN1 dt. That equals Vf exponential negative delta Gm over kBt, just like before. But this time, jumping backwards from 2 backwards to 1, you've got this extra term, right? You have your regular activation energy you have to overcome. That's this part up here. So an atom hopping from site 2 back to site 1 has to overcome that, but it also has to overcome that delta mu, our chemical potential difference. And if that's large, then you can really bias atoms to hop from site 1 to 2, but not be able to hop back from site 2 to 1. So we take into account both of these. The total, or the net diffusion from site 1 to site 2 is dn1 dt minus dn2 dt. And if there's only a small difference in the chemical potential, we can simplify this expression to simply, that's this symbol, that's gamma, that's capital gamma multiplied by delta mu kBt. Let's change color. So let's now talk about flux. Again, flux was the number of something per unit area per time. That is a flux. So flux for us, we need to take into account 1/6 times n dn dt. 1/6 comes from a cubic orientation. We're assuming a cubic orientation for a moment, right? Where if you're talking about a flux in one direction, let's say in this direction, then of all the 6 different directions that an atom can hop, it could hop up, it could hop down, right, left, right, in the page and out of the page. Only this direction right there is moving us in flux in one direction, right? So that's where the 1/6 comes from. N is the concentration, so that's some number per volume, but we're going to multiply that by the distance that it jumps. And then you've got dn dt, right? That's the concentration gradient, the change in the concentration with respect to time. Okay? dn dt. All right, over here then, we can rewrite that since we know what dn dt is. We solved it from before, right? This was our dn dt. We can go ahead and we can plug that in. So we've got 1/6, right? N is our concentration. We'll just call that C now. And then you've got, that's the concentration times the jump distance, right? So N, that whole thing there, that's N. And then lambda times that was our dn dt. That's a change in our concentration with respect to time. Okay? Or again, you could rewrite that in terms of the gradient. So now that we've got some of the basic math in place for how this sort of happens, let's talk about the mechanisms. Diffusion can happen via different mechanisms. What it's going to rely is atomic motion jumping from site to site. Therefore, we have to have the following conditions. First, there have to be adjacent to an empty site. If you're going to hop from one site to another, it has to be an empty site. Imagine students. If I took one student and he's surrounded by students that have filled seats, he can't jump into their seat, right? Second condition is the atom must have sufficient energy to break the bonds with its current neighbors, cause a lattice distortion during displacement, right? And this is where the activation energy comes from, right? Requires activation energy. It takes a little bit of energy to break those bonds and to push atoms out of the way a little bit during the deformation, okay? So now we have 2 different ways that we can achieve this. One is vacancy diffusion, and this means that you're going to exchange the atom with a site that is already vacant, right? So imagine in the classroom, if there's an empty seat and a student sitting next to it, the student could hop from that seat to the empty seat. That would be an example of vacancy diffusion. And we know that vacancies themselves, they are a function of temperature, right? We know that the fraction of empty seats, NV over N, equals the exponential of negative QV over kBt, right? So the higher the temperature, the more vacancies there are, and therefore the more vacancies there are, the more likely you might say, okay, vacancy diffusion is going to get easier and easier at higher temperatures because there's more vacancies, okay? And then one last thing to note here is that the atom and the vacancy travel in opposite directions, right? They exchange places, so they must travel in opposite directions. Now the second mechanism for diffusion is what's called interstitial diffusion. In interstitial diffusion, that's where you're migrating some sort of atom from an interstitial site to another. And interstitial sites, by definition, are already unoccupied, right? Now, if you start to fill them up, then you have to worry about occupancy. But most of the time, they're going to be relatively empty. Now, because interstitials are small, you're talking about holes between packing of atoms, then you probably are only going to get small atoms involved in interstitial diffusion. Things like carbon, nitrogen, hydrogen, those tend to move pretty well via interstitials. Okay? So a question that we'll pause really quickly and discuss among students is, which do you think is going to be faster? which of these mechanisms will be faster, vacancy diffusion or interstitial diffusion? Okay, I hope you've had some good discussion and pointed out that obviously interstitial should be faster for two reasons. First off, the bonds holding it between the atoms around it are weaker. You have weaker bonds with an interstitial atom, right? Because it just got plugged into a lattice that was already bound in the first place. And then for the second reason is you have a higher fraction of unoccupied sites. More empty sites. You don't have to wait for a vacancy when you do interstitial diffusion because most of those sites were already empty, right? So for that reason, interstitial tends to be much faster than vacancy. All right, let's now turn our attention to solving two different types of diffusion. The first type that we're going to talk about is what's called steady state diffusion. Steady state. What steady state means is that it is not changing with respect to time. With respect to time. So it's a steady state. It's not changing with time. Again, it's going to be a flux, which means it's going to be the number of something per area per time. The number that we're going to do, we're either going to do number of atoms. You can do that as literally number of atoms, or you could just talk about it in terms of moles. Either is fine. Per area per time. And to talk about steady state diffusion, we introduce Fick's first law, right? Fick's first law is the following. It says that J, our flux of the diffusing atom, equals negative D. D is the constant of proportionality for diffusion, which we call the diffusion coefficient. We're going to come back to that later. So negative D, the diffusion coefficient, multiplied by dC dx. That's the gradient in concentration, right? C is your concentration, so dC dx, that's how the concentration is changing with respect to position in your sample, right? So again, if we go back to our two bars that we welded together, our copper bar and our nickel bar, there was a really steep gradient at first because it went from pure copper to pure nickel. So it had a really strong driving force for these things to start mixing. And then as they slowly mix and dC dx goes to 0, you lose your driving force. And eventually these things would just mix perfectly if you gave them enough time and temperature. Okay? So now let's consider a material that's separating two different gases with different partial pressures. So we're going to draw our axes like this. We're going to draw on the vertical axis, we're going to draw concentration, and on the horizontal axis, we're going to draw position, right? So let's say that this is your sample. So this whole region here, that's, let's call it a metal. And then over here, on the left-hand side, you're going to have a different pressure than on the right-hand side. So let's call on the left-hand side of this metal, let's call this the side A. We'll call that this has a pressure A, and this has a pressure B, and we'll know that pressure B is less than pressure A. So if you're trying to put, say, carbon dioxide in soda to carbonate it, if you go to a higher pressure, you're going to dissolve more of that gas into the soda. Well, the same thing happens here in the metal. You can dissolve some of your gas into the metal. It's going to go into the interstitial sites, or maybe it'll occupy the vacancies, but it's going to dissolve into it. And the higher the pressure, the more that's going to be into it. So let's say that the concentration right here at this surface of dissolved gas in the metal, we'll call it Ca, right? And then over here, because it's a lower partial pressure, we'll say that concentration is just Cb. We'll call this XA, and we'll call this point XB. Okay? Under steady state conditions, meaning that it's not changing with respect to time, the concentration in the sample itself, in the metal, will be linear. That will be linear, right? And the reason we know that it's linear is as you're diffusing atoms from the left to the right, so the flux of atoms, that's the direction of flux. We're moving atoms from site A to site B, right? We know that that's J is equal to negative D dC dx, right? The fact that this is linear, that right there, you could solve your diffusion coefficient from that slope, right? If you knew what the concentration profile looked like in your material at any given time. Okay, so dC dx, that's just going to be Ca minus Cb over Xa minus Xb. So let's go ahead and take a look at this. Imagine hydrogen gas purification across a thin palladium sheet. You can actually do this. If you take a thin sheet of palladium and you've got a difference in your hydrogen partial pressure on either side, you could actually move hydrogen from one side to the other to purify it, right? And again, steady state just means that the gas concentrations, this point Ca and Cb, that those aren't changing with time, right? And therefore the slope is linear. So where do we get this d value from? D, that's our diffusion coefficient. That's going to be equal to d naught multiplied by the exponential of negative q, that's an activation energy, we'll call it qd for the activation energy for diffusion, over kT. So there's many of these examples where it's yet another thermally activated process where the higher the temperature or the lower the activation energy, the more of whatever it is we're talking about. In this case, we're talking about diffusion. So higher temperatures or lower activation energy means higher diffusion. And then you have a constant out front, which has the right units, right? That's the pre-exponential, right? So you could look this up for lots of things. Here's a table from our book. For example, if you're talking about iron diffusing, that's the diffusing species, and the host is iron, then here's your pre-exponential with the right units. Here's your activation energies, and you use those for different values, basically, different temperature ranges, okay? Or here's some typical values, excuse me. If you're talking about carbon diffusing here, again, carbon is interstitial. So that's interstitial versus self-diffusion, basically. This one's going to be much faster. Yeah, sure enough, take a look at this. It's going to be much faster. Okay? And then you could even talk about carbon diffusing in ferrite versus austenite. And again, it's going to be faster for the carbon in the more open lattice. Okay. So let's do an example. I'm going to have you work this out with the TAs, but first let's get it started. It says you're working for Intech and your job is to harden titanium by the diffusion of carbon. The concentration of carbon at 1 millimeter into the surface of the titanium slab is 0.68 kilograms per meter cubed, and at 3 millimeters the concentration is 0.25 kilograms per meter cubed, right? So that's our two concentrations. The temperature of the carburizing environment is 925 Celsius. The rate at which carbon is entering is this 2 millimeter thick region is 1.27 e to the negative 9 kilograms per meter squared per second. What is the diffusion coefficient for this particular treatment? So I'm going to pause this video and work on the solution while you guys work on it with the TAs. Okay, hopefully you came up with the same answer we did. On our end, doing J equals negative D, dc dx, that's Fick's first law, which we know to use because this is steady state conditions, right? Okay. Let's see. That is equal to delta C over delta X, and that's CA minus CB over XA minus XB. So we punch in our flux here, right? We're given the flux. We're told that it's a 2 millimeter thick region, right? So it's 1 millimeter minus 3 millimeters. That's the 2 millimeters, right? Oh, sorry, that's supposed to be in meters. There we go. Up here you've got the two concentrations, 0.68 minus 0.25. That's kilograms per meter cubed. When you start to plug in everything, you're going to end up with D equal to 5.9 times 10 to the negative 12th, and that should be in meter squared per second, which is the correct units for diffusion coefficient. Okay. So that first part, this was for steady state conditions where it's not changing with respect to time. We're now going to change that and talk about non-steady state diffusion. Changing with time. So it might start out diffusing fast, but then it will maybe slow down, or maybe it'll slow down and then speed up for some reason, right? So non-steady state diffusion can help explain that. There's some really cool examples of that. I'll have the TAs explain this video for you.
Greetings, fellow nerds. In this video, we're going to perform the classic chemistry trick of turning pennies into silver and gold. First, get 30 grams of zinc sulfate. Then add 100 milliliters of water and turn on the heat to get to boil. As it's going, add in a few strips of solid zinc metal. Please check the video description for where I got my chemicals. Now get a copper penny, or any piece of clean copper for that matter, and drop it in. It has to touch the zinc metal for the reaction to occur.
Okay, so far, Now you've got copper touching zinc in a solution with zinc sulfate. So you've got zinc ions. So I want the TAs to sort of facilitate a discussion on what you expect to happen as you heat this up a little bit. It's touching, you have the electrolyte, what should be happening? Okay, let's see if you got it right.
What's happening is the zinc is reacting with the copper and dissolving, while delivering electrons into the copper. The copper, now charged with electrons, will reduce free zinc ions into zinc metal on its surface, giving a silvery color. This takes about 10 minutes, so I'll skip over that. Here you can clearly see the more silvery color of the penny. Now look at that. We've just turned a...
So they took zinc from solution and they plated it onto the copper. So the zinc ions were reduced, right? They reduced zinc ions to plate them on there. The zinc ions 2+ picked up electrons to become zinc metal, and now it's sitting on the surface.
copper penny into a silver one. Sure, it's a trick, but it looks cool. Now for the most amazing trick, turning it into gold. Let me wash it first. Simply put the coin directly onto the hot plate, heated to about 300 degrees Celsius. As it heats up, the zinc diffuses into the copper and produces a yellow burn.
So zinc is diffusing in. Why? Because there's a concentration gradient. There's less zinc in the copper layer of the penny. So zinc wants to travel in. It's moving down the concentration gradient. And as it does so, it turns into brass, right? Brass is a different color. So it's not turning it gold. It's not turning actually into gold atoms. It's just turning gold color because it's turning into brass. And again, this is driven by diffusion.
Brass. At first it's going to look coppery, but that's because it's still hot. After you cool it directly with water, it will now appear gold. Don't try to pawn this off as actual gold, though. The brass layer will eventually wear off. Anyway, that's the trick of turning copper into silver and then into gold.
Okay, so you saw that happen. In real time, you could see those atoms diffusing in, right? So this is a great example of non-steady state diffusion. It's changing with respect to time, right? So for example, if this is your concentration, at first you might have let's say you're maintaining the concentration at the surface, right? And in the inside of your sample, deep within your material, it's some very low value. At first, you're going to have most of it at the surface, right? You might have something like this. But as you do this longer and longer times, it's going to slowly start to approach the steady state condition, right? Non-steady state will slowly approach steady state if you take into account time. So because of that, we now need a new expression. We need to use what's called Fick's second law. Fick's second law is dc dt equals capital D, our diffusion coefficient, but now this is d squared c dx squared. So you have the first derivative with respect to the first derivative of concentration with respect to time, and you have the second derivative of concentration but with respect to x position. So this is, if you've taken PDEs yet, partial differential equations, and you know how to solve these, here's the basic approach. You set it up, you have to apply boundary conditions, and then you use a generic solution is the approach. In this class, you won't have to solve the PDEs. We're going to give you solutions, but this basically tells you the situations where you can use the solution. First off, you have to say, okay, before diffusion, any diffusing atoms are uniformly distributed at C0, right? So if you have some sample, the diffusing species are already distributed. They don't have to be zero, but it has to be evenly distributed. You then say at x equals 0, that's the surface, right? At t equals 0, time t equals 0, the diffusion begins. And then your boundary conditions are, okay, at time t equals 0, the concentration equals the initial concentration for all points in the material. And for all times greater than 0, the concentration is held at some surface concentration at the surface, x equals 0, and it stays at its initial concentration deep within the material, right? Those are your assumptions you're making here. And from that, you have this solution. If those conditions are valid, then this solution can be used to model how the concentration is changing in your sample with respect to time. So it's a little bit of a complicated solution. Let's take a look at this. You've got Cx. That's your concentration at any position x. Right? You have C0, that was your initial concentration everywhere. Cs, that's what the concentration is at the surface, right? Then you have 1 minus ERF. ERF stands for the error function. And that's a mathematical tool that we're not going to get into. You can read more about it here at the wiki page on it. right? And inside the error function, what you're going to take the error function of is x, your position, whatever you're trying to figure out, the concentration at some position x, that's the x we're talking about, divided by 2 times the square root of dt, where d is your diffusion coefficient and t is time, okay? So it's not the worst thing ever to use. It's a little bit tricky. The hardest thing about these, I find, is people using the error function table correctly, right? If you have a calculator that can calculate error function, that'd be one thing. Most of them cannot, and so you have to calculate it by hand. So here's how you do it. If this is z, then this is the error function of z, right? So in this case, everything inside of here, all of that would be z, right? And so if you wanted to figure out the error function of z, this table gives it to you. However, it only gives it to you at discrete values, at a bunch of individual points. It doesn't give it for any arbitrary point. So for example, what if you wanted between, I don't know, say these 2 points? What if your value of z was 0.18, right? How do you know what the error function of z is? Well, if you remember this from at some point you would have learned this, probably college algebra, that if you have 2 points, point here and point here, and you want to find out the point in between at some arbitrary position, we can do so. So for example, this is x1 and that's y1, that's x2, y2, but you want to figure out your points at x and y, you can apply the linear interpolation formula, which is given as follows. That y minus y's, let's see, this would be y1, I guess, over x minus x1 equals y2 minus y1 over x2 minus x1, right? So using this formula, the linear interpolation formula, you can figure out any value you need to in this error function table, right? So that's how we handle that. Now there is something else that I'd like to cover before time is getting short today, and that's this idea of a general diffusion distance. But I'm going to preface this by saying caution. Caution. Definitely, people make mistakes on this every year. This general diffusion distance is just a back of the envelope approximation, right? This is just an approximation. That it's basically like saying the average. The average diffusion distance is going to be square root of d times t. If you want to figure out the actual diffusion distance, or the distance at which you're going to have some specific composition, use Fick's second law. Use this solution to Fick's second law, right? Almost always, this is what you should be using. I'll make it clear by saying, give me a very average ballpark, back of the envelope. I'll use words like that when I'm talking about an average diffusion distance, and that's when you can use this. This is just an approximation, and you could actually see what we're doing here. We're plugging in an average value for x. We're basically saying here when the error function is equal to a half, right? So it's when you are half the way between your surface composition and your deep inside the material composition or concentration, okay? All right, a few last things to cover before we're done for the day. First one is, what are the factors influencing diffusion, right? Well, first off, the diffusing species is clearly going to play a role. So consider self-diffusion of alpha iron at 500 degrees Celsius, right? So here's your diffusion coefficient, very, very small. 3 times 10 to the negative 21. That's a really slow diffusion, right? But carbon diffusing in that same lattice is going to be massively faster, right? It's equal to 2.4 times 10 to the negative 12. So that's like, what? That's 9 orders of magnitude faster. That's 1 billion times faster. Carbon moving in the lattice versus iron trying to move from vacancies in that same lattice is going to be 1 billion times faster. So diffusing species definitely plays a role. Another thing that matters is temperature. We've already said that this is a thermally activated process. We know the equation looks like this, that D, our diffusion coefficient, is equal to D naught, the pre-exponential value, exponential, the negative activation energy over RT, or KT is really better there. It depends on, so again, if this is given on a per atom basis, then this should actually be KBT. Right? So that's your diffusion coefficient. It should depend on temperature. And again, just as before, we could make this nonlinear expression look linear, right? If we took natural log of both sides, we'd get natural log of d equals natural log of d naught minus qd over r multiplied by 1 over t. Or in other words, if you plot reciprocal temperature, this is, 1000 over temperature, right? And you plot the diffusion coefficient on this side, you could figure out the activation energy from this slope. This slope, that's equal to negative q over r, right? That could be r or kBt. Depends on if you're talking about per atom or per mole of substance. Okay, let's do another example. Let's say that boron is pre-deposited at 4.5 times 10 to the 20 atoms per centimeter cubed on a silicon wafer. So the initial concentration of the silicon wafer is 5 times 10 to the 15 atoms per centimeter cubed. That's how much boron is initially present in your wafer. And you obviously put lots more at the surface, right? So here's your surface concentration. Here's your C naught initial concentration, okay? Conditions are 30 minutes at 1223 K, and you're given the diffusion coefficient, and you're given it in microns squared per hour. So calculate the concentration at the diffusion length, right? So again, diffusion length, that's when we're talking about this ballpark, x equals square root of dt, right? So let's go ahead and do that. Let's say that's going to be equal to, well, actually we'll have the TAs work on this with you, and we'll see if we get the same answer. Okay, when you go ahead and plug this in, you find that Cx minus C naught over Cs minus C naught equals 1 minus the error function of x, which we're told is just the diffusion distance, square root of dt, over 2 times square root of dt. So the square root of dt actually cancels out. We're left with just the error function of 1/2. Going back up to our table, the error function of 1/2, that's an easy one because it lands right on it. We know that inside if z is 1/2, 0.5, then the error function of z is 0.5205. So we've got 1 minus 0.5205. Rearranging, we can say that Cx is given by this expression, and solving for Cx, we have that it's 2.15 times 10 to the 20. So that's less than what was at the surface, right? The surface had 4.5 10 to the 20, but it's way higher than what was in the initial material, okay? So that's an example of using Fick's second law for non-steady state diffusion. Now, if there's time left, we can go ahead and work on this next example, which is there a temperature at which copper atoms in pure copper will diffuse at the same rate as zinc atoms in brass? So I'll have the TAs help you set up this question. Okay, so to set this question up, it's actually pretty straightforward. You know that the diffusion coefficient, D equals D naught, exponential of the negative activation energy for diffusion over RT. So all you have to do, if there is a temperature at which they're the same, you're just going to write two equations. This one for copper and copper, change that. This one right here, that's for copper and copper, and this one is for zinc and copper. The only thing you don't know is temperature. Setting those equal, you could solve for the temperature and figure out if there's a point at which they would be the same. All right, the last thing to cover for today is the short circuit diffusion paths. We might be close out of time, so you might want to catch this on the YouTube video afterwards, but short circuit diffusion paths is interstitial and vacancy mechanisms. Those are what we call bulk mechanisms for diffusion, but there are other faster ways to diffuse. For example, if you move along the surface, you're going to have really fast diffusion because there's lots and lots of empty sites, and there's less strain that you're imposing on the lattice to hop along the surface. Volume is the slowest, that's hopping in the lattice either through interstitial or vacancies, and then in between are grain boundaries where there's lots of open space, and this is like students probably walking down the aisle right now as class is ending, where you have more open space, and so diffusion rates are going to be faster along grain boundaries generally than the volume, and surface is going to be faster than both of those. And then the last thing we'll say, faster diffusion for open crystal structures. If you have a lower melting point material with secondary bonding, all these lead to faster diffusion, and slower diffusion for close packed structures, higher melting, covalent bonding, big atoms, ions, more dense, right? And we'll cover this diffusion in liquids and gas at the start of next class period.